Talking about chemistry today, Carl. I took chemistry in high school. To make it more exciting, I created a game. I would ball up pieces of paper and try to shoot them into the trash can from various distances around the room. At the time, that's how I thought you made chemistry exciting. No, my teacher actually joined in the game. Hi, welcome to episode 4 of Living as Nature, the series in which a non-scientist, me, draws on science, as well as other disciplines, to develop a better philosophical understanding of our place in the universe. Today, we're going to talk about chemistry, molecules, and solar systems, and how these things make possible our very own pale blue dot, the planet Earth. As a quick reminder, our telling of the universe story is very far from the whole story. Even experts in physics don't know the whole universe story. I'm focusing on a few central developments that demonstrate how entangled our stories are in this grand story. So I'm leaving a lot out, and I'm not going as in-depth as I could at any one point. I'm hoping you're learning a lot, but I also hope, like me, you're learning how much you don't know. Especially you, Carl. When we left off in our universe story, process 3 stars, or first-generation stars, were creating heavier elements through nuclear fusion. By doing so, these stars planted the seeds for greater forms of complexity in the universe. But heavier elements were only part of the story. To understand why, we need to talk about chemistry. Sorry, Carl. Force of habit. In its simplest definition, chemistry refers to the structure of matter, in particular atoms and molecules, and how it interacts, combines, and changes. Chemical interactions were happening fairly early in the universe story, when the first hydrogen and helium nuclei combined to form the first molecule in the universe, helium hydride. For our part, we're going to focus on 2 types of chemical interactions: ionic and covalent bonds. Through these interactions, atoms and molecules can join together through various processes to form more complex structures. So how do these chemical interactions work? No, seriously, Carl, I'm asking. I didn't do a lot of research for this video, so do you know? Recall from earlier videos that an atom is a nucleus of protons and neutrons, or just a single proton with no neutrons in the case of a typical hydrogen atom, orbited, again for lack of a better word, by 1 or more electrons. We know what element the atom is by how many protons are in its nucleus. In other words, its atomic number. But to better understand chemistry, it's important that we talk about a few things we haven't yet discussed when it comes to atoms. First, ionization. Atoms have electrons, as we know. Electrons are bound to the positively charged nucleus by the electromagnetic force, which, you'll recall from episode 2, creates attraction between things with opposite charges. When an atom has the same number of protons and electrons, it has a neutral charge. This is what we're looking at with atoms on the periodic table. However, under the right conditions, electrons can break free of their relationships with their nucleus and join other nuclei. This process is called ionization. And the result is that the atom either has more electrons than protons or more protons than electrons. And so it is either negatively charged or positively charged. These atoms are referred to as ions. A positively charged ion is called a cation. A negatively charged atom is called an anion. Second, electron shells. Why does ionization happen? I've said before that electrons orbit the nucleus of an atom. It's more technical to say that they inhabit different probability mists in different shells. It's a bit wordier though, Carl. Different elements have different numbers of shells, distances or spaces where electrons can hang out around them. You can tell how many shells an atom has by looking at the periodic table. You know, Carl, that table was a lot more useful than I thought it was when I crumpled it up and threw it in the trash. From 20 feet away! Woo! On the left-hand side, you'll see that the rows of the periodic table are referred to as periods, ranging from 1 to 7. This refers to how many electron shells atoms of that element have. The shells are numbered sequentially N1, N2, N3, and so on. So, hydrogen and helium both have 1 electron shell, N1, whereas carbon has 2 electron shells, N1 and N2, and silicon has 3 electron shells, N1, N2, and N3. Above the table, you'll also note that the elements are categorized into groups, ranging from 1 to 18. Groups 1 and 2, and 3 through 18, are referred to as the main group elements, while groups 3 through 12, which include the lanthanides and the actinides at the very bottom of the table. You know, Carl, I used to struggle a lot with actinide when I was in high school and college. Still do sometimes, actually. Oh, that's not what that means? That's embarrassing. Are referred to as transition metals. We're going to focus on the main group elements for now. The outermost electron shell of any atom is called its valence shell, and electrons in that outermost shell are called valence electrons. Main group elements in the same group have the same number of valence electrons in their valence shell, and this number increases from left to right. So, one way to think of this is, different elements in the same period are filling up their valence shell with electrons as we move from left to right. Now, each electron shell has a maximum number of electrons it can hold based on its energy level. N1 can hold 2 electrons, N2 can hold 8 electrons, N3 can hold up to 18 electrons, N6 can hold a whopping 72 electrons. Don't be too impressed, Carl. I have good intel that those N6 shells are doping. However, valence shells, again that outermost electron shell, tend to be happy and stable when they get 8 electrons, regardless of whether they are an N2 or an N7. This is referred to as the Octate rule. The exception is N1, which is happy with 2 electrons in its valence shell. Go helium. In the inner shells, electrons have less energy. They can just sit on the couch, Netflix, and chill. Electrons like this and tend to fill up the inner shells first. That's the opposite of students in my class, Carl, who fill up the outer shell of seats first, and then only begrudgingly move inward toward me. With an infusion of energy, for example from a photon or from a collision with another atom, electrons can become excited and jump to outer shells. Electrons can also lose energy, become unexcited, and jump to inner shells. No, Carl, I don't think electrons watching this video are all dropping to their inner shells. Also, you suck. Third, valence electrons are key. As noted, each shell that electrons can inhabit have space for only a certain number of electrons. When this space is filled, electrons can't join the party. However, in the valence shell, when there are open spaces for electrons to move around, chemical bonding becomes possible. With the influx of enough energy, a valence electron can leave an atom altogether. He didn't deserve you. You're better off without him. And I don't think you're going to be alone for long. And with open spaces in a valence shell, electrons can join the party or bind atoms together. More on that in a moment. So what happens if an atom has its valence shell filled? In that case, it's pretty content with its situation, and it's less likely to interact with other atoms. So if you look at the periodic table, you'll note that the elements in group 18, which have 8 electrons in their valence shell, are labeled noble gases. And like Carl on first dates, they aren't known for their interactive properties. Seriously, you suck. As a reminder, helium only has 2 electrons, but it also only has 1 electron shell, N1, which can only accept 2 electrons. So it's happy and content with 2 electrons. All this suggests that, if you get the right conditions, including atoms with flexibility in their valence shells, situations conducive for atoms to move around and interact with one another, and sufficient free energy for electrons to become excited, you can get some cool chemistry going. No, Carl, I don't think you should start a singles dance club called Valence Party. Wait. Could work. Dibs. And these conditions can happen in space, typically within a certain distance from stars. Not too close where heat would be prohibitive, and not too far away where the lack of heat would be prohibitive. This is called interstellar chemistry. Chemistry is important to the universe story because it creates complexity from simple building blocks, that is, atoms. And stars, because they produce such a variety of atoms, provide a wide variety of building blocks for this process. The universe has a whole Lego set to play with. These simple building blocks, atoms, are put together to make more complex structures, molecules. You'll recall from episode 3 that a molecule is a group of atoms bonded together through chemical interactions. Molecules are the base unit of a substance. For instance, sucrose, or table sugar, is a chemical compound of 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms in a particular structure. That means that one molecule of table sugar, represented as a model, will look like this. Chemical synthesis produces molecules, and molecules can also combine, producing more complex molecules. All of this contributes to even more complex structures, including, eventually, life. Let's put these pieces together by using an example. An atom of sodium has 11 protons and 11 electrons. Sodium is in period 3 on the periodic table, meaning it has 3 electron shells, N1, N2, and N3. It's also in group 1, meaning it has only 1 valence electron, 1 electron in its outermost shell. The math is mathing here because N1 can only take 2 electrons, and N2 can only take 8 electrons. That's 10 electrons. There's only 1 electron left, that goes to the valence shell. Math! Sodium is not the best at holding on to its valence electron. Baby, come back. You can blame it all on me. I was wrong, and I just can't live without you. Sodium can live without that electron, but It's nice to be dramatic sometimes. Chlorine has 17 protons and 17 electrons. Like sodium, chlorine is in period 3, so it has 3 electron shells. But it's in group 17, meaning it has 7 valence electrons. Again, the maths. Remember that 8 valence electrons makes a stable set, so chlorine is always on the hunt for an extra electron to reach stability. Now, if a chlorine atom is able to snipe the valence electron of a sodium atom, which often happens, they both become ions. The sodium is now positively charged, a cation, because, having lost an electron, it has 11 positively charged protons and only 10 negatively charged electrons. The chlorine is now negatively charged, an anion, because it still has 17 positively charged protons, but it now has 18 negatively charged electrons. Electromagnetism draws the oppositely charged ions together to form a bond. They now stick together as a neutrally charged molecule of sodium chloride, or what we call common table salt. Because this chemical bond involves 2 ions, we call it an ionic bond. Fun fact, a single grain of table salt holds about 10 to the 16th molecules of sodium chloride, formed together in a crystal lattice structure, or this number. Man, I love that tune. So, when you eat salt, think about how many molecules and how many atoms you're eating, all held together by electromagnetism because of ionization. There are several other types of chemical bonds, including covalent bonds, metallic bonds, and polar bonds. In a covalent bond, rather than one atom losing its electron and another atom gaining it, or stealing it, I said what I said, Carl. Atoms can simply share an electron while singing Kumbaya. It's just beautiful that they can do that, you know? For instance, in a water molecule, 2 hydrogen atoms join together with an oxygen atom. 2 on 1. These atoms are frisky, Carl. On the periodic table, oxygen is in period 2, so 2 electron shells, and group 16, so 6 valence electrons. That means it has 2 valence slots open. Hydrogen is period 1, so only 1 electron shell, and group 1, so only 1 valence electron. Because N1 can only hold 2 electrons, hydrogen has 1 valence slot open. By joining forces, the hydrogen atoms can each share their 1 valence electron with the oxygen atom, and the oxygen atom can share 1 electron with each hydrogen atom. In this symbiotic relationship, each atom, in a sense, fills their valence shell and becomes stable. Covalent bonds are very important for life, as they tend to be instrumental in carbon bonding with other elements. More on that in the next video. Let's take a step back. The elements that were created in stars and blasted away can gather together in galactic clouds. Similar to nebulae or nebulae that form into stars, galactic clouds are collections of dust and gas, containing mostly hydrogen and helium. But galactic clouds are significantly larger than nebulae. In fact, you can find nebulae within them. And unlike earlier nebulae, these clouds have heavier elements in them because of the death of process 3 stars. Denser regions of these clouds form molecular clouds, which have simple molecules in them as well as dust, clumps of solid matter. The force of gravity can cause the densest areas of these regions, solar nebulae, to collapse, forming a star. An instance of this occurred roughly 4.6 billion years ago. Like Carl, when an appetizer is delivered at a restaurant, this star, our sun, devoured over 99% of the available matter. But the rest swirled around at a distance, flattened into a disk by gravity. Solar wind, which refers to a stream of charged particles produced by our sun that sweeps across the solar system, pushed lighter elements such as hydrogen and helium further out, essentially creating 2 zones of elemental composition. In the inner zone, there was a rich diversity of elements, including a good balance of heavier elements. The outer zone was composed mostly of the primordial elements of hydrogen and helium. Gravity went to work on this matter floating in space through a process called accretion. Mass accumulated together through the pull of gravity and collisions until eventually asteroids, moons, and planets formed. In the outer zone, which had mostly hydrogen and helium, large gas planets such as Jupiter and Saturn formed. In the inner zone, smaller rocky planets, Mercury, Venus, Earth, and Mars, formed with heavier elements such as iron, silicon, and magnesium. That's how our home, this pale blue dot, as Carl Sagan called it, it's nice to know there are Carls of excellence out there, formed. It was the rules of chemistry, the interplay between the electromagnetic force, the structure of atoms, the tendencies of electrons, and so on, that made this jump in complexity possible. Let's not forget it was also the formation of heavier elements in process 3 stars. Collectively, these aspects of the universe come together to form our planet. They also make possible the next chapter of our universe story, life on Earth. We'll start to address that chapter in the next video. Until then, farewell. I can't do a big noise. Wait, let me try again. I'll just oink. I'll just oink.